Hello, my name is Brayden. I'm a second-year undergrad in Caltech, researching in the planetary surface processing group. And today I'll be talking about how we can use probabilistic modeling to estimate the risk of river migration and develop a river risk map. So as you already would know, that rivers meander, and this is a beautiful example in the UKLI River in Peru. And within just a few years, you can see how much the river erodes and deposits the nearby sediments. Now imagine that there's a local village or an important ecosystem nearby the river. Is there a way to assess whether that land will get eroded in the future year? In other words, is there a way to predict the meandering of rivers? For that, we must come to the use of probabilistic modeling. Now, you are probably all familiar with probabilistic modeling. It helps us forecast the future by looking at the frequency of particular events that happen. So I live in Pasadena, so I'm pretty familiar with the earthquake risk map. If you live in the East Coast, you might be familiar with the hurricane risk map, or if you live near the coast, the urban flood map will be more relevant in the upcoming years. So how do we implement a probabilistic model for river erosion? Now, it's not a traditional probabilistic modeling in a sense that river erosion is not static. If you look at earthquake, we can determine the frequency in a given length, and we look at the past 100 years and see how much earthquake happens, and that we can derive the frequency. However, rivers are dynamic. We must predict the river first, and how we do that is we use some type of numerical simulation, and we develop various different scenarios of possible river erosion. Then we look at the frequency based on the prediction. So getting to the river meander modeling, we must know some physical modeling. So one of the things that we know is that the local migration rate is dependent on the curvature, the bend radius divided by the river width. This determines the bank erosional rate. We also know that erosion rates are influenced by the upstream channel geometry, and the erosion rate increases as you go downstream. And the Howard-Knudsen model, which was published in 1984, describes this model. So the total migration rate is the combination of the curvature model plus the weighted upstream value, and this is a second approximation. And MeanderPy is a numerical simulation that was developed by Dr. Sylvester in UT Austin that does just the Howard-Knudsen model. You can see that initial channel is the UKLI River, and given some inputs as function, you can see the river meanders through time. So let's get the probabilistic distribution based on this model. We have the initial channel, which is the blue line you can see here, and given some time, the river channel changed to the orange channel. Now we have a distribution of variables. For simplicity of MeanderPy, let's say MeanderPy is a function of input migration rate, which is the rate of migration, and Chezy friction factor, which is the sinuosity of the river. The higher the Chezy friction, that increases the bendiness of the river. And then we have time, and that creates an output. And we have a distribution of those variables, and let's say these are normal. So given a one random run, we get this particular prediction. And let's do another run, and we get this particular prediction. Okay, so we have the first one was an underestimation of the actual river change. And the second one was an overestimation, and this is kind of self-explanatory. And within the distribution is the coverage of the potential erosional area. Now this is not a problem. This is not a probability. You can't say that one area has a more likely chance of getting eroded compared to another area. So just to repeat, we run multiple channels with two primary input, which is migration rate and Chezy friction. What we use is Markov chain Monte Carlos, or MCMC, and we get a conditional probability. And this is based on what best matches the modeling output and the final river channel. So if it runs a simulation, and if it best matches the orange channel, then the error rate would be almost zero. And the MCMC would know that that would be closer to the truth value compared to an overestimation that we did in the previous run. And we can use this PDF, or probability density function, to forecast future river channel. Now let's do synthetic river testing. This basically, we have an initial channel, we run MeanderPy for some time step, and we get an initial and a final time step. The reason why we do this is we have the initial and the final condition, and we know the truth value of the migration rate and the Chesney friction factor. In this case, the migration rate is 300 meters per year. I made it very dramatic. Chesney friction is 0.01, and the time step is 10 years. This is how standard numerical modeling is done. If we look at Bayesian inference, it's kind of different. We have an input and output channel as the input. We have the time, we have the amount of time step that we want to run. And instead of having the function of parameters, we have the Bayesian inference. So we have the posterior equals the likelihood, which is, given that equation. And what we should theoretically expect is a normal distribution of migration rate and Chesney friction at a mean of 300 meters per year and 0.01. So running the MCMC model, it does just that. On the top right, the top left is the migration rate. And it starts out all over the place, the migration rate, but it converges to 300. The bottom is Chesney friction. It's 1 because it's x times 0.01, so it does converges to 0.01. And one of the closest you can see is the right graph, the right top left. You can see the migration rate kind of starts at a mean of 200, but it knows that it's underestimating the truth value. So it's increasing the migration rate, and it's seeing that the error rate decreases, so it later converges to 300. And Chesney friction, you can see, is kind of narrowing it down. That's the Bayesian inference learning as it does the simulation, and learning that the certainty is more likely within that narrower range. Now, using the PDF, we can do a risk mapping of rivers. So we run the numerical model n times using the infrared parameter values. So we get this cluster of potential likely values. We run it n times, let's say 100 times. Then the p erosion is the number of times the river channel crossed the location divided by that number. And here's the risk map of the synthetic testing. And you can see that the potential area, the 1 means that out of the 100 times that it ran, that area, the river has touched that area 100 times out of 100. That's why it's 1. 0 means that the testing of the river never touched it. That's why it's 0 out of 100. And in between is how much the river has crossed, the actual river has crossed over our risk map. So that shows the probability. Now, using this applying this to a real system, it gets a lot more trickier. You saw earlier that UKLI River is a lot more complicated in its erosional movements, and so currently we're working on adding more parameters to the MCMC to make the truth value more closer to what the actual truth value may be. And then this is one of the work in progress that we have with the UKLI River. You can see it's a lot more noisy, and there's a lot of cutoffs in the value. But as of now, we're testing this method that we developed to the particular case of UKLI River, and we're also working on the appropriate time scale of this forecasting, and also the scale, how big of a river can we forecast, or the accuracy will decrease, but if we zoom into like a particular bend, the accuracy will increase. So what is the appropriate length scale and time scale for forecasting the system? So in conclusion, we developed an algorithmic scheme to generate river erosion risk map. And synthetic river shows that the MCMC converges to the truth values of the parameters that we knew. And the river erosion risk map can forecast uncertainties explicit, and therefore can reliably predict river migrations. I'd like to thank my collaborators, which are Omar, Kieran, and Mike. And here are my fundings. And if you have any questions, particular technical questions, that is my email and my website. And thank you for this presentation.